Hello guys, welcome back to my channel. After a long break, I sincerely apologize. This summer has been really more productive for me than any of the summers before. So with that, let's get started. Um, the the question that we're gonna try to solve today is an integral. So integral from 0 to 1 of natural log of minus natural log of x to the epsilon minus 1 divided by square root of minus natural log of x dx. So one natural thing that you would sort of do looking at this is use a U substitution, sort of set U equal to whatever it is inside the parenthesis, or is sort of the argument of the major functions here, namely the natural log and the square root. So because if you do that, dx turns out to be negative e to the negative u du, if I'm not wrong. And then I is just integral from 0 to infinity. Or maybe I shouldn't skip so many steps. Infinity to 0. Natural log of u e to the minus u epsilon minus 1 divided by the square root of u negative e to the negative u du. Well, we can use the negative, sort of correct the upper and lower bounds. 0 to infinity. Natural log of u, this e to the u will e to the minus u will cancel off with the e to the u here. Maybe I'll use a pointer. So this the e to the u generated by this minus 1 will cancel out with this e to the minus u that we have here from the integration factor. So with that, we have e to the minus u epsilon as a surviving exponential over square root of u du. Fair enough. Then we have 1 over epsilon. If we use the substitution u epsilon equals w, such that du is dw over epsilon, integral from 0 to infinity of natural log of w over epsilon e to the minus w over square root w over epsilon, or dw. I'm just plugging everything in there. I'm not doing anything fancy as of now. Square root of epsilon, I should write it in a different way, over epsilon, integral from 0 to infinity. We can use a property of the natural log soon, because we have natural log of w minus natural log of epsilon. And with this exponential factor and the square root of the integrating variable here, which is w, we can split this up into two integrals by linearity. So you have 1 over square root epsilon integral from 0 to infinity of natural log of w e to the minus w square root of w dw minus square root epsilon integral 0 to infinity natural log of epsilon e to the minus w over square root w dw. Fair enough. We can sort of write these things in a different way. This is I1 and that is I2. What's I1? Actually I2 is the easiest to figure out. Let's do I1 first. So I1 is how do we work with this? Well, remember the gamma function. Gamma of z is integral from 0 to infinity of e to the minus t to the z minus 1 dt. If we differentiate gamma with respect to z, going to end up with e to the minus t to the z minus 1 and a natural log of t dt. And now if we set z equals to 1/2 here, gamma prime of 1/2 e to the minus t with t to the z minus 1 and z is 1/2. 1/2 minus 1 is minus a half, so that becomes a square root t in the denominator with a natural log of t and a dt. And you notice we can change t with w, it doesn't matter. We literally have I1 here, so this is I1 precisely. This is just clever observation. And now by definition, gamma prime is just gamma times the respective digamma. It's a product of those two things. Well, what's gamma of 1/2? Well, it's gamma of 1/2 is square root of pi because it becomes the Gaussian integral upon resubstitution. Now to find the digamma of 1/2, I might have to use a different formula. So maybe I'll sort of also change the color. So I can use the duplication formula for the digamma easily. You can get this by using Legendre's duplication formula and then converting all the gammas to digammas. Or you can just watch a video if you don't want to go through the entire trouble of doing everything. So if we set s equals 1/2, we have 2 times digamma of 1 equals 2 times natural log of 2 plus digamma of 1/2 plus the digamma of 1, because 1/2 and 1/2 make 1. We'll have digamma of 1, which is minus Euler-Mascheroni, equals 2 times natural log of 2 plus digamma of 1/2. So digamma of 1/2 is precisely Euler-Mascheroni minus 2 times natural log of 2. Fair enough, we know that now. So our integral I1 was just gamma of 1/2 times the digamma of 1/2. Just becomes square root pi with a minus digamma plus 2 times natural log of 2. Sorry, this is not digamma, it's Euler-Mascheroni constant, my bad. Euler-Mascheroni constant plus 2 times natural log of 2, all multiplied with a negative of square root of pi. Well, the other integral isn't really bad to do, and by the other integral I mean I2. Let's recollect what that is. I2. So in I2 we have a natural log of epsilon that will come outside. So I2, as I said, natural log of epsilon will come outside. Integral from 0 to infinity e to the minus w over square root w dw. We can sort of rewrite this in a more suggestive form. W to the 1/2 minus 1 dw, because writing it such enables us to see that this is actually gamma of 1/2, which is the Gaussian integral over entire range, so it's square root pi. And we finally have a nice formula for ourselves right here. We know what I1 is, we know what I2 is. So we just have to multiply with a 1 over square root of epsilon up front. And we have a pi as well, so to account for. So we can write in a better way. Square root pi over epsilon. And we have this term with a plus sign, so natural log of epsilon minus all this other junk we have. Euler-Mascheroni minus 2 times natural log of 2. We can rewrite this, suck up the negative, like we always should have. We get this Euler-Mascheroni plus, my bad, there was actually a minus here because I2 was subtracted from I1. So if we account for that, everything just comes out. We have 2 times natural log of 2 can be written as natural log of 4. And then this, you add this natural log of epsilon, so this becomes natural log of 4 epsilon. And that's pretty much it. That is the answer we were looking for this integral. So this is just square root pi over epsilon with the minus Euler-Mascheroni plus natural log of 4 epsilon. Okay, so just a quick note here. I1 needed special knowledge and good observation of the fact that this was gamma prime of 1/2. So you needed knowledge of gamma function. There is, and I believe, I haven't tried it myself yet, I believe there's another nice way of doing this using sort of like the complex analysis of multi-valued functions, because we have a natural log here. And with the same spirit, I promise I'm going to revisit some of the old integrals of the past that were improper and contained multi-valued functions like the square root or natural log or stuff like that, because now we're armed with the idea of the multi-variable function theory from complex analysis. It's going to really help us simplify lots of things. So see you in the next video, hopefully. In the meantime, peace out, stay tuned. I will try to be more frequent, but please bear with me.